I want to do an experiment. I want to see what happens if I accidentally walk past the end of an array. So I've drawn up my array A here. I've declared it in my code. It's got 3 elements. And at index 0, I've got the value 10. At index 1, I've got the value 20. At index 2, I've got the value 30. And we know that internally, once you create the array, all that's really ever tracked is this pointer to the beginning. And that's why it's important if you pass the array into a function that you also pass its size, because it's the programmer's responsibility to make sure that they don't use elements of the array that don't exist. It is an error to attempt to use index 3 of this array. The problem is, the compiler lets you do it. It's a logical error. You'll be marked down for it on an exam, but the compiler lets you do it. It's your responsibility to make sure you're only working with valid data. But what happens if you don't? What happens if you forget? It's very common to write code that accidentally goes one element past the end of an array and reads a value that doesn't exist or writes a value that doesn't exist. So what do we do in a case like that? Well, obviously, debugging a case like that can be pretty tough. It might require tracing by hand. And certainly, we shouldn't be writing code that does that. But if we can write it, and if it runs, what is actually happening? So I've made up this test program, which has a whole bunch of variables, x, y, and z, an array A and an array B. And I've just drawn out the array A. I want to use it as the subject of my experiment. I'm going to print out all the data in the program, then I'm going to do something, then I'm going to print it out again. And that's the whole program. So I'll start by running it in its original form. Okay, so it prints out the same things twice. 6, 10, 17, 10, 20, 30, 900, 901, 902. Here is what I want to try. I want to see what happens if I walk past the end of this array. So we know the last valid index of the array is index 2. If I walk past the end of this array and I set index 3, let's set it to something really recognizable, 1, 2, 3, 4, 5. If I set index 3, does anyone stop me? And if they don't, what happens? Okay, so we'll compile it. Nobody stopped me. And now I'll run it. And we know that there are things you can do that will compile, but when you try to run the code, the program crashes. Is this going to be one of those things? When we run it, doesn't crash. The program runs, it finished it successfully. The operation I did, which is before it prints the word after, well, that apparently had no trouble because I print the word after. But notice that when I'm done, that value, 1, 2, 3, 4, 5, that's actually an element of B. So what happened? Well, when you declare variables in your program, it's the compiler's job to figure out where to put those variables in memory. And formally, it's none of your business. So we don't care. We can't assume the compiler is doing anything in particular. There's no necessary logic behind it. Obviously, the compiler has reasons that it does things the way it does. We have no reason to know those things, and we shouldn't expect that every compiler works the same way. In this case, it looks like what happened was the compiler put all of the elements for B right after the elements for A. When you create an array, the compiler does guarantee you that all of the elements for the array will be together in memory. They'll be right next to each other. That's why pointer arithmetic works. But the compiler doesn't give you any assurance about where it puts B or where it puts the variables x, y, and z. And it turns out if I walk past the end of A, well, A doesn't have an index 3. But the way that we interpret an array index, as we know, is basically pointer arithmetic. This is saying, this subscript operation is saying, follow the pointer from A and walk forward by 3 steps. Okay, so I follow the pointer, 1, 2, 3. And then I store the value 1, 2, 3, 4, 5. Okay, great. I can put something there that's somewhere in memory. It just happens that this is actually, secretly, the first element of B. And so I might have gotten in the way of other data that I need by doing this. That's one reason we should never write code that does this deliberately. But we should understand that because the computer's memory is actually pretty simple, and because the C language is actually pretty simple, it's not doing things that are magic. It's just working with data in memory. And if we run off the end of one of our arrays, we might end up accidentally stepping on some data we're using for something else. Okay, what happens if I try walking off in the other direction? So what if I go to index -1? So whatever comes right before A in memory. I set that to 1, 2, 3, 4, 5. Okay, well, in this case, afterwards, B is still intact, A is still intact, but Z contains that value. So it looks like when the compiler made space for all the variables, it put Z right before the elements for A. And you might look at that and say, that doesn't make sense. I declared Z after I declared A. So it's none of your business. The compiler has some internal order that it uses, probably either for the convenience of the compiler writer or maybe for performance or something. It's up to the compiler where it puts those variables. If you want to use the variable z, use its name. Don't go find it in memory. And the key here is if I walk off the end of an array, I'm stepping into unknown territory. And it's possible that that unknown territory, if I'm close, so if I just walk one step off the end of my array, it's possible that that unknown territory is just more of my own property, like the beginning of B. If I walk a little bit further than that, if I walk off the end of B, maybe I'm still stepping on stuff that belongs to my program, because the compiler puts all sorts of stuff into memory that we don't know about. Internally, the compiler has to keep track of things like what function are we in, and when the function returns, where do we return back to? That's all done for us. That's a service that's provided by the runtime system and the compiler. But it keeps that data in memory. And if we walk too far off the edge of our array, we might end up stepping on that important data. But I guess it's also true that if we walk too far off the end of our array, we could end up sticking a number somewhere where it doesn't make much of a difference at all. So for example, let's set a sub 10. That's quite a ways past the end of A. It's even past the end of B. We'll see what happens if I set that. Okay, ooh. Something pretty ugly happened. Okay, what if I set a sub 100? And in this case, for some reason, it works. So notice that when I set a sub 10, I guess whatever it was I stepped on was valuable. And so the program broke when I modified that value. But if I walked even further away from my data, everything seemed to work. And just to be clear about that, let's try setting element 123. We'll set it to 9999. And then I'll print something out. I'll go off and do something else. You know, this is some output. And then I'll take a look at what's in that value. Now we know A does not contain this index. This is an invalid element of A. But if I wander off past the end of A and I just stick a number somewhere into memory, so there's 9999, it could be that there's nobody else that needs that piece of memory. It could be a deserted area, and if I put something there, no one will notice. And that's the risk I'm taking. That's one of the reasons we should never walk past the end of an array. But we should understand what really is going on when I walk through arrays or when I walk past the end of them. The value is, and we'll print out a sub 123. All right, we'll save that. We'll try running it. We'll see if it crashes. We'll see what else happens. It looks like it prints out the value. No crash, nothing else. We went one step over and we ended up stepping on B. We went 10 steps over and we ended up stepping on something valuable and the program crashed. We went 100 steps over and apparently nothing happened. So what's actually going on? What it comes down to is in the computer's memory, which is massive. There are billions of elements in the computer's memory. In the computer's memory, there are spaces available for every program that's running. And those programs have to coexist. And they also have to be kept from conflicting with each other. The operating system handles that. It makes sure that your program can't get in the way of some other program. The operating system makes sure that when your program runs, your program gets its own little chunk of memory to work with. And that in general, you have to stay on your own property. If you walk outside of your yard and you begin digging, then we don't know what's going to happen. That is undefined behavior. If you walk into the neighbor's yard and start digging a hole, well, I guess there's a few options. One of them is maybe you live next door to a vacant lot and nobody notices. That's what happened here. I use an index way off the end of my property, but nobody seemed to notice. Maybe they didn't notice now, but they might notice later. Another option, of course, is that maybe you walk into the neighbor's yard and you start digging and the neighbor is home and they're not happy. And we saw what happened if we did that. And it's also possible that you could walk so far that you just end outside of the known universe. You could walk so many steps outside of your own property that you're not just on your neighbor's yard, you have left the known universe. And in that case, even then, the operating system is watching and it can step in and prevent your program from doing any actual damage, or maybe from engaging in some kind of malfeasance. It could be your program was deliberately looking outside because maybe it wants to get into the internal memory of some other program to do things like exploit some sort of security vulnerability or look at the values of a password or something. It's hard to describe this in greater detail without talking about memory, because we can't talk at a low level about computer memory, but fortunately, I do actually have an analogy that might work for this. So suppose that I have a function with a scope. So let's say my entire screen is the scoping box for main. And inside main, I've got this array A. And I want to see what happens if I walk past the end of the array. So just to be clear, we shouldn't be doing this, but we should have some idea of what bad things could happen, bad things, if I do. Okay, so I want to write an assignment like A sub, I don't know, 6, of course, equals 10. Okay, so what does that mean? Well, I follow the pointer A and I walk 6 steps ahead. 1, 2, 3, 4, 5, 6, and I set that to 10. Now, this is not actually an element of A. It's something. It's space. It's space that still belongs to main. It's inside the box for main, but we don't know what it is. It could be empty. It could be completely unused. It could be some other variable in main. It could be a piece of data the compiler is keeping, for example, where to return back to when main finishes, something important, or it could be unused. It's a risk I'm taking. Of course, it's not a risk I should be taking because I should just create a new variable or make a bigger array if I need the space. But if I accidentally walk past the end of A, I end up here. And the operating system wouldn't care. My program might break. Maybe it won't, but it might. But that's not the operating system's problem. It says whatever you do inside your own property is your business. If you want to burn your own house down, that's not a big deal with me. It's only if you get onto somebody else's property that we have a problem. So here I'm modifying something in the scope of main, which probably isn't a good idea. It could break a lot of stuff. Maybe it wouldn't be obvious immediately even. It might be that whatever's in here that I just stepped on, I don't need again for a few minutes. And only when I try and use it again do I see a problem. That can be a real nightmare to debug. What if I set A 100 to 10? Okay, so A sub 100. Okay, each of these elements is about 2 centimeters. A sub 100, I would walk off the edge of my screen, and then I guess I leave the scope of main, but I'm actually only going to end up, I guess it's hard to tell you how my house looks, but I'd end up in my kitchen, I think, if I walked about 100 steps in this direction. Okay, so I'm in my kitchen. Can I set something to 10? Absolutely. It's my kitchen. I can do whatever I want. It's none of your business. And it's none of the operating system's business either. If I walk off the scope of main and end up in the scope of some other function, well, that's probably a really, really bad idea. But it's still not a problem for the operating system. Again, if I'm burning my own house down, not a good idea, shouldn't do it. But the operating system has a pretty laissez-faire attitude towards that. It lets me do that. Okay, but what if I go even further? What if I leave my property? Now, I live in Victoria, so I don't have a kitchen big enough to, how about, I wouldn't even need a value much bigger than 100 to do this, but if it's worth doing, it's worth overdoing. How about 10 million? Okay, so I start at A. 1, 2, 3, 4, 5, 6. Okay, so I sat down and worked it out, and I think 10 million would put me, if it's 2 centimeters apiece, puts me 200 kilometers away, which would be in the middle of the ocean off of the Olympic Peninsula. Okay, so there's Victoria up there. And here I am down here, which is not only in the middle of the ocean, but I think I've crossed a border, so that might have violated international law. And the operating system says, what are you doing? You have tried to go to a place that doesn't exist, that's so far outside of the comprehension of any program that there just isn't anything there. Of course you can't do that, and it punishes me, obviously, for that. It says your program is completely off the rails by setting that element. Okay, fine. But what if I do something sort of in between? So not 10 million, okay. How about 500,000? Okay, 1, 2, 500,000 would only put me 10 kilometers away. That's fine. It looks like we're on land. And that's the middle of the naval base. And this time the operating system has a different issue. So it's the same in real life, I guess. If I were to suddenly materialize in the middle of the naval base, they would call the authorities and they would have some questions for me. And I would say, well, I'm just teaching arrays. This is a C course. And they would say, oh, it's just Bill teaching arrays again. And this is a modern democracy. They would throw me in jail or something like that. I'd get a lawyer. The operating system doesn't work that way. If you walk into somebody else's memory, you end up somewhere you're not supposed to be. You're on somebody else's property and you try modifying their stuff, It'll swoop in, the authorities will be called, and the operating system will punish you. But the operating system is not a modern democracy. The operating system has only one punishment available, and that is immediate termination. And so if your program tries to act outside of its authority, in memory that it does not own, the program is immediately terminated. And that's where the operating system gives you that cryptic warning, segmentation fault. That's actually just it telling you your program is done. It is done right now. And that's because at that point, the program can't logically continue. If this operation can't be allowed, nothing else the program is going to do could be allowed either, because they all could depend on this invalid operation. Now, basically inside of, especially a course like 111, but inside of a C course, the solution to problems like this is pretty simple, which is always make sure you make your arrays big enough, and make sure that when you're debugging your code, when you're writing your code, and when you're testing it, you trace through it a couple of times, you make sure you're not walking off the end of an array. But there are times you encounter cases where the program randomly crashes. You get that segmentation fault warning. On Windows, you might get a, this program has stopped working, or something like that. And that might be because, obviously, you didn't intend to use 500,000, but maybe you used index I. And by accident, I ended up with the value 500,000. That can be pretty frustrating. And unfortunately, in a language like C, there are tools called debuggers that can help you a bit with this. But often the solution is print out values of variables every now and then as you're testing to narrow down where the problem is happening. And then in some cases, just try tracing through it to isolate the cause of the problem. And as we come to the point in the course where we work with things like strings, where memory issues can often show up a lot, it's important to make sure that we're proactive in debugging. We write code that's well tested and well documented. We use lots of functions and write them correctly, because that can really help us and prevent having a debugging disaster show up later.